Good afternoon, everyone. My name is Femi, and I'm here with my group mate Amara, and we are here to discuss the energy losses in a fire tube steam boiler and a low power steam turbine. Boilers and turbine systems generally make use of the Rankine cycle to generate energy. The Rankine cycle consists of four distinct processes. 1. The isentropic compression in the pump. 2. The constant pressure heat addition in the boiler. 3. The isentropic expansion in the turbine. And lastly, the constant pressure heat rejection in the condenser. It is important to know that these two systems, the boiler and the turbine, are connected through a piping system, which is described in the diagram below. Boiler system losses. The process of heat transfer in steam generation results in a numerous amount of losses. Losses may be caused by moisture content in the fuel, the high temperature of the stack gases, the material's low conductivity, and the impurities in the feed water. Every boiler-related losses directly affect the amount of fuel consumed, which raises the operational cost and reduces the efficiency of the boiler. Forms of boiler losses. The most common form of boiler losses are losses due to dry flue gas. Secondly, another form of loss is the heat loss due to moisture in fuel, heat loss due to incomplete combustion, loss due to excess air, and blowdown losses. Here is a diagram that directly describes the amount of heat losses in a boiler system. As you can see, the highest amount of loss in this boiler system is the heat loss in flue gases, which consists of about 18 to 25%. And after the numerous amount of losses, the overall system efficiency is reduced from 100% to about 50 to 70%. So now we move on to calculating the heat loss in a boiler system. So we calculate the heat loss by multiplying the values of the area, the difference in temperature in the inside and the outside surfaces, and the value of the heat loss. It can be represented using the formula heat loss Q equals to K, which is the thermal conductivity of the material, times the area of the material, divided by L, where L is the thickness of the boiler, multiplied by the difference in the internal and external temperature. Here we calculate the maximum heat loss from a boiler of wall area 6 feet square and thickness of 0.12 asbestos. The thermal conductivity of the boiler is 0.1 BTU per height feet degree Fahrenheit. If the internal and outer surfaces of the insulation is assumed to be 1600 and 500 degrees Fahrenheit respectively, so we tabulate all these values and the heat loss is going to be given as 5500 BTU per each feet squared. So I will hand over the floor to my group mate to discuss the energy losses in low power steam turbines. Thank you.
Thank you, Femi. Good afternoon. So I will be talking on the energy losses in a low power steam turbine. So to do this, I have to come up with the problem description. The turbine in this case is a single cylinder steam turbine where steam is coming from a steam generator, more like a boiler, and after work is done in the turbine, the steam is then directed to a steam condenser. In between these 2 points, we have 5 extraction points, and we are going to do the whole analysis of the turbine and be able to come up with the energy lost in this turbine. The process in this turbine, because it's a real life scenario turbine, is a polytropic process. So, and we are also going to calculate for the ID properties as well. The difference between the ideal process and the actual process is going to give us the energy lost in this turbine. As a matter of fact, the real process and the properties at this point in this our study is taken from a steam power plant in Jordan that was which we made reference to in ISAM journal article. To go forward, we have to make some assumptions in this turbine. One, that this process in this turbine is a steady state flow, and also that the potential and kinetic energy changes in this turbine is negligible. It is also important to note that we are not assuming that there is no heat loss or heat gained in this turbine. Going forward, the first equation that will help us in this our analysis is Q in minus Q out plus P in minus P out plus En in minus En out, where Q as a terminology stands for the heat gained. If it's Q in is heat gained to the turbine, Q out is the heat lost by the turbine, the power in is the power into the turbine, and the power out is the power done by the turbine. The En also stands for the total power of the operating fluid flow. This total power of the operating fluid flow is gotten by the mass flow rate multiplied by the specific enthalpy of the fluid flow. We also have the standard energy efficiency given by En in minus En out. The real or also known as the polytropic power is given by equation 4 in this slide, and the ideal power is given by equation 5 in this slide. The difference, as we can see, is that in the ideal power we are actually making use of the ideal property, specific enthalpy property of the fluid, which is gotten from steam tables, while the real specific enthalpy is gotten from our reference journal. The exergy of this fluid is given by EXI is equals to MI times EXI, where I here in this our study represents the operating points. Which can either be 0.1, 0.2, 0.3 or 0.4, and the EXI is given by HI minus HO minus TO multiplied by SI minus SO, where O here refers for the ambient conditions. The H and the S are gotten from the HO, and the SO is gotten by using the ambient conditions, where ambient condition is referred to the standard temperature 298 Kelvin and pressure, which is 1010 raised to the power 5 pascals. So after making use of this, we come up with our table. Result of our analysis gives us table 1, which is the parameters of the ideal steam expansion process and the parameters of the expansion process. So from our tables, we're able to come up with our specific enthalpies and specific entropies at temperatures and pressures. The result gives us that after we've done our analysis, we find out that the actual power produced by this turbine was about 43,952.89 kilowatts, while the ideal power from our calculation gives us 58,595.37 kilowatts. Therefore, the energy lost by this turbine, which is the difference between these two power, was given as 14,462.4 kilowatts. The efficiency of this turbine was given to be 75%. This efficiency falls within the range of other low power steam turbines that has been described by previous researchers. So in conclusion, we see that the calculated energy loss and efficiency of the whole turbine does not show any potential problem, as the values we have are in the range of other comparable low power steam turbine. We also recommend that for the boilers to optimize efficiency and reduce heat loss, that the carbon, amongst other points, that the carbon coming out from the furnace can be rejected into the furnace for complete combustion to take place. Thank you so much, and thank you for listening to us. Thank you.